right, so I'm going to go ahead and get started. My name is Alex Roschli. I'm a researcher at Oak Ridge National Laboratory. I work at a facility called the MDF, which is the Manufacturing Demonstration Facility. If you're not familiar, it is a government research lab. The MDF is a DOE user facility, which means we're kind of open to the public. We work directly with American industry and non-American companies as well, but primarily American industry, doing research and development on a variety of topics, mostly geared towards advanced manufacturing, but with a heavy focus on additive manufacturing. But we do have traditional composites work, machining, hybrid manufacturing, that sort of thing. As some of the other presenters kind of alluded to, additive manufacturing is not the solution to everything. And so we have all these traditional manufacturing methods, and we use additive manufacturing to show how we can improve those processes and how we can work together to do more manufacturing and improve the entire landscape. So some quick background about me. I've been working at the MDF for about 11 years now. Most of my work is on large-scale manufacturing. Originally did a lot of polymer work, thermoplastics, got a little bit into thermosets, transitioning more into large-scale metals, the DED, wire-based processes. So here's a variety of the projects that I've worked on now. Today, most of my work has moved towards slicing and the software that runs slicing, which is kind of the overarching thing between all of those projects you just saw pictures of, is that all of those are printed with the same software. It's a Toolpath generation software that we have developed at Oak Ridge National Lab. We use it for, like I said, all these large-scale processes, and we kind of keep growing it out into new applications, new systems, new processes. So for those that aren't familiar with slicing, it's kind of the step, the process to go from your solid body CAD model all the way out to your finished part. So it includes creating your faceted model, be your STL or your 3MF. You know, we're hopefully going to get away from that triangulated mesh soon. Dewan's leading the charge over there. But you know, move towards better geometry representation and try to improve this process. Next step is going to be slicing, and then from there you're going to fit your toolpaths for the layers, print the layers. You know, if all that goes well, you're going to have that finished part at the end that looks very similar or identical to your CAD model. So a bit of background for this project, or for this presentation rather. You know, the idea is always out there that we can 3D print anything, right? And there's a lot of truth to that, but there's a lot of failures to that as well. There's a lot of things we can't do, or a lot of things we've tried to do and haven't succeeded on. And so you saw those projects I have done. How many of those worked the first time? How many of those worked the second time? How many of those took us a long time to do, and how many things did we end up having to redo over and over and over again? And so one of the more famous ones of those is the first 3D printed car, which is at the top, and I'll show a picture of it again later. But before we printed that car that looks great and it kind of traveled around the world and was a rather successful project for us, we made this car. And this is obviously significantly ugly. There's got cracks in it everywhere. There's huge gaps. The armrests have holes in them large enough I can put my arm through the armrest. The fenders can be pulled apart with your hands. This is a printed part that's supposed to be able to survive like an impact, but you can just go peel it apart. So this was the first car. This was 7 days of printing around the clock. 7 days of people at the machine maintaining it, all for this part that really isn't a success. And how could we have improved that? How could we have had better software, better computational design, better tools to understand what we were going to do before we did it, and to try to prevent that failure? And so this right here, this project, the car was finished in 2014. This print right here was late June, early July of 2014. Like I said, it took 7 days. By the time we made the actual one, we were able to print the whole thing in about 2 days. And so printing faster was part of the solution. But redoing the design, better understanding of the toolpath, better modeling of the whole printing process and of the car is really what helped us get there. And so I'm going to step through a few various aspects of the software design, specifically towards toolpathing. The first of those is looking at infill pathing and this applies mostly to polymer systems, but you do see infill on some of the larger metal processes as well. And so for those who aren't familiar, the traditional infill pathing approach is going to be you project a pattern, lines is the most common, over your object for a layer. You clip it to the boundary, and then you join it all together, and now you've got this pattern. Pretty simple, works great, but it's all uniform. And how many of our parts are going to get used in a uniform way? This is a square. If you make a cube, that's a pretty good example. You use that pretty uniformly. But as you get to larger objects, more complex shapes, they're all going to have different loading. Certain areas are going to see more load than others. The loading from the side might be more than from the top. And so how do you accommodate that? How do you design for that? How do you simulate that? And so that's kind of what we've been working on. The left side of this is what you just saw, the conventional method of generating infill where it's completely uniform. And the right side is looking at how to model and simulate that. How do we iterate through that infill until we get an infill pattern and an infill design that's going to work for the actual end use application of the part. And so looking at areas of high stress, and so doing tighter infill, doing these a honeycomb pattern, but doing a much smaller, tightly packed honeycomb, than areas of low stress, trying to spread that out, use less material, print faster. And then as you see, there's going to be a connectivity issue if you're just putting those two, if you're just drawing those uniformly and putting them next to each other, it doesn't quite solve the problem. So you have to iterate through that, and you have to be willing to modify and kind of change the structure and the layout of all of those to make them blend together. And so here's how that kind of works for us. The simulation for this is all done through Abacus. So you load in your object. In this example, we used a very basic structure for an aircraft wing. Simulate the loading on that, find the areas that's going to have high stress, areas of low stress, and then start doing an infill patterning over that whole process, or over that whole shape, specific to the stress analysis. And then once you've got that infill pattern, go back in and simulate it. Simulate what the infill pathing is going to look like and kind of iterate through that until you have a solution that looks workable. And then the last step of all that is trying to validate and do some testing. And so the patterning algorithm is primarily done with circle packing algorithms. So filling the whole space with circles, big circles for areas of low stress, small circles for areas of high stress, trying to pack that infill more tightly. And then looking at that grid, trying to understand where you need, like I said, the large circles versus the small structures, or large circles versus small circles, to fill that adequately. And so looking at all of those as they apply to the actual design, the very first one on the far left is going to be your uniform infill pattern. So all those hexagon shapes are the exact same. It's just like the lines, it's a pattern projected across the shape, then it's cut at the boundaries and everything's connected together. The next one is looking at the iterative circle packing, so putting circles in there and changing the size of the circle to get the optimal fill in there. The next step, sectioning, trying to look at the areas of high stress and low stress. And so you can see a very distinct area that's going to be the high stress. It's got those tightly packed hexagons. And then the last one there, trying to combine those approaches. So now we have a variety of hexagon sizes, and they kind of morph together to give you this more complete infill pattern across the whole structure. And so then looking at what happens when you load it, when you put the weight on there and see how does it deflect across all these different designs. And so the picture at the top there shows just the basic uniform infill, and then the very last one, the iterative plus the sectioning approach. And then here's kind of all that data moved together, ultimately showing that with the iterative plus sectioning approach to that infill pattern generation, you get about 50% higher stress for that same shape. Next thing I kind of move into is looking at how you control the toolpathing on a more site-specific level. How do you do different things in different areas? And how can the user design this from the software? Maybe you don't have the ability to simulate what you want to do, but you know close enough to what your end use of the application of the part is going to be. And so this example you see at the bottom, looking at the mold for an Iron Man mask. So you've got the mask, protruding from the front, and so we want to do something different just in the area where we've got the mask. But the rest of the structure, we don't need it to be as high resolution. Maybe we can print it faster. Maybe we can use a different material. So trying to identify that area, and so the second image there shows in orange, this is the area we want to do something different, and how do we want to control that? And so in a lot of our applications, it's just as simple as changing the print speed in that area. So printing it really slow, trying to do a higher resolution. You can change the layer height. You can change the bead width, so you can put really thick beads there. If you're going to machine it, it gives you more material to cut into. And so the user can design all of this, and it takes about the same amount of time in the slicing approach. Still, 5 seconds to slice this object once the user sets it up. And the last image there showing you can make the whole part hollow with a slicer. One of the speakers mentioned it yesterday, kind of the issue with CAD and the offsetting process. That not a problem when it's in slicing because you've got it at the polygon level, the offsets are very easy. Whereas CAD for these complex shapes, doing the offset, trying to make the exact thickness you need, can be a lot more challenging. So just a quick look at some of these as how they would have been built. The one on the left has been machined to give you that nice solid surface. Another use for this, looking at site-specific control, this is on a large-scale metal process. If you print that bottom right object, it's just a plus-shaped design. The way the bead, the weld bead, is going to move around those corners, you're going to have a porosity in the middle. You're going to have that that void space. So what if we can keep the same pathing, but we just modify the welding parameters when we get to the center of that, so we get a more solid object, but we can keep the print speed the same. We just change the power of the lasers. This is made out of titanium using a laser wire system, but the user can go in and define that central area. We need to do something different here. Another application of that is what we call embossing, so being able to change the parameters, again, in a specific area. In this instance, you can project an image or project another object onto the surface and then just change the parameters in that specific area. So again, on the bottom, that's the same system. It's a titanium wire, projecting the ORNL leaf on there and then just changing the weld pool parameters while it's going through that area to emboss a shape. So here's the car again. As you can see, it's a printed one big monolithic structure, and then seats have been added in. But as software has progressed and the machine has progressed a lot as well, what if we could print those seats in? How would we go about doing that? If we wanted to do a more comfortable material, the original one is just a solid bench with like a divider down the middle between the two seats. But how would we tell the software we want a specific material there, or we want to print that area differently? So the settings regions are part of that. And that kind of leads into doing multi-material toolpathing. So being able to do specific materials in specific areas. This is useful for mixing rigid and flexible materials, but also mixing lightweight materials, low-cost materials. So back to the Iron Man mask, if you want to do the tool surface out of a very high expensive material, if you're printing the whole thing out of metal, you want to use tool steel for that surface, but the rest of it, you want it to be cheap. You could use mild steel, and so you just designate that surface as one material and the rest of it design it as the other. And so this can all be designed by the user through the software. Again, foams is another great one, looking at variable density. And so here's kind of a more look at that. This is on a large-scale thermoplastic system. The top right, it's that same structure you saw from the infill. Rather than using the same material for the whole thing, what if we did PLA for the areas that we needed high stiffness, but out in the low stiffness areas, we mixed in a foam, so it prints. It's even lower cost, less weight, but still one machine, and it's all blended through. And so we can functionally grade those materials through the software by designating. We can load in the loading applications into the slicer, and so apply those. The bottom left there is kind of looking at a different process. This is what I was talking about earlier, combining additive manufacturing with traditional manufacturing. And so printing material directly into a mold, and then as soon as you turn off the extruder, you throw that mold into a stamping press. So we've got a 500-ton press, and so you can compress the object, get rid of all those voids and deformities, but you can still have a good solid object. And you can do localized material control. So we mixed orange and black material there. The black is going to be your carbon fiber ABS, so it's much stiffer but much more expensive, and you can use it just in the areas that you need it. Just a quick on the foams. We've got two types of foams we can use. One would be a syntactic foam, so trying to blend in your actual resin material with a foaming agent to give you a material that's still pretty stiff, but it's lightweight. So looking at density of less than 1 gram per cubic centimeter, so something that's going to float. And then if you want to go really low density, really inexpensive material that you're just trying to fill an interior structure, looking at expandable microspheres, so foams that when they come out of the extruder, they really expand. And so designing that into an object. This right here is a tool for precast concrete. I'll show it on the next slide, but it's actually a building that's been built here in Brooklyn. But the important tooling surface, make it out of your expensive material or carbon fiber, but the rest of the interior structure where you just need a little bit of support, use your syntactic foam to design the material properties and to lower that cost. And so on the right there is just a quick look at what that image of that building looks like. It's I think it's on the south waterfront, but the whole building needed about 200 different of these precast concrete molds to make all of the exterior architecture pieces. All those concrete molds that go around the windows, it's meant to kind of deflect the light differently no matter where you look at it to shine like a sugar cube. It's built on the location of an old Domino sugar factory. And just a look at the system for how that was done. It's a thermoplastic system, Cincinnati BAM. It's got dual material infeeds, and so it can switch those materials right at the infeed to the extruder. But there's also a blending unit, so that's how you do the functionally graded materials. If you want to go from that PLA to the PLA foam, you can blend those materials as you feed them out to the extruder, so you can change that density. And so a look at how the software works. This is, again, a simple square shape, but simulate your material, simulate your object in Abacus or whatever you prefer. Then you can load it, take out that data, and you can load it into the slicing process and then apply it to your infill. And so that's what this is showing here, is that every step of that infill is going to have a different material recipe applied, and so you can grade the material through that infill structure. Last thing I want to talk about is trying to figure out how to print faster, how to do different pathing structures. So basic figure 8 shape here, the way this is going to be traditionally printed is 3 closed loop paths. You got one for the outside and then one for the around each of the openings in the center. So on a large scale system, at the end of a path, you have to slow down as you go into the end of the path. You have to wipe the tip, you have to lift up, you have to travel to the next path, you have to lower down, and you have to start again. It's a lot of time. It's a lot of wasted time, a lot of wasted machine time where you're not printing. So is there a way we can improve that, where we can kind of combine all this together and print it faster? So that's looking at a single pathing approach. And so a really easy way to do it is just go in and cut your CAD model, but that takes a lot of time. It's a lot of manual labor to go in and modify the object and cut it. But if you have the software go in there and optimize it, you can cut it in these different locations. Then you can move those cuts layer to layer. And so that's what you see in these images. The one on the left is kind of showing really narrow tool pathing, so you can better see the gaps, and the one on the right is actually showing the real bead widths. And when you print that, in reality, you're going to overlap them, so you still have that strength there. And this is just looking at some more complex shapes. The one on the left, you really exaggerated the cut distances, so you can see where they are and basically turning those paths around. And this is fully automated, so you load in your object just as you would normally design it, and then the software will design all these cuts in, it'll cut it, and significant time savings. The object in the top center there is the cross-section of a boat hull. The time savings on that is about 30%. And then the object on the right is what it would look like if you wanted to leave all of your outer contours as solid. You don't want to cut any of those. So around all of your holes, you have a solid contour, and then you combine all the interior pathing to speed that up. And the way this works on infill, and this is going to tie back to what I talked about first, is using a continuous pathing algorithm for your interior structures. And so using the Chinese postman problem, once you've got that circle packing done and you've got each of those circles as a node, how do you travel through each of those nodes optimally? How do you try not to replicate any of those? You don't want to go to the same one twice, so how do you move through the whole thing optimally? And how do you have the software design that and simulate that and then print that? And so this is what it looks like. The one on the left is your traditional pathing. So it's going to do one big outside path where it kind of meets the contour, and then all the interior ones are all these individual closed loop paths. You can see the blue highlights this. We're going to have to stop and you have to travel and move to the next circle, because every single one of those is going to be printed individually, whereas on the right, printed much faster. It's combined all of those together to one homogeneous path. And so the time savings on this object, kind of an extreme case, is about 50%. And then here's what it looks like if you print it on small scale. So on a small scale printer, the time savings is not as significant. There's a lot less of that wiping the tip, slowing down when you have a filament system, because you can pull that filament out to cause retraction and stop the material flow. But on thermoplastic systems, when you got pellets and things like that, you can't just stop the flow as easily, because you can't spin it backwards. You're going to pull molten material up into an area where you shouldn't have it. And so the small scale systems definitely can go a little bit faster and have less of a need, but still very applicable. But with that, thank you. I'll be around the rest of the afternoon if anybody has questions.